Okay, let's continue. So we're done with now cosine and sine functions. What's next? What's next? So we can do something else. For instance, we can do, let's say, e to the power negative at and cosine bt, for instance. Okay? This is something we have seen before. The Fourier transform is relatively simple to find out, but here, you know, it's not that easy. But we can still do. We can still do. Because what you can see here is, well, instead of having e to the power jt and e to the negative jt, we can again write it as what? E negative a plus j of t plus e, again, negative a, negative j b of t. And the rest is pretty simple. So first term will be 1 over s plus a minus j. So we should apply negative sign, so that's why we have a minus j. Second term, s plus a plus j. We have 1 there. And of course, everything should be multiplied by 1/2. Multiplied by 1. And the rest is simple. We can put them together. S plus a on top, s plus a squared plus b squared underneath. Okay. Which is quite simple. Now, it should be noted that here we have product of two individuals, and it's not equal to a Laplace transform of each individual, the product of the two individuals. Okay. They're not equal to each other. And in general, we cannot do this directly. Cannot do this directly. Now, in the textbook, in the fifth edition, in page 349 of the textbook, you can find a table 7.2, I believe, which summarizes, a number of Fourier transforms. I'm sorry, Laplace transform of some important, and fundamental basic functions. Again, in the final exam, you may want to include them, to make sure that you understand them correctly. Okay. Let's continue. Now, as far as the properties again of the Laplace transform, as we discussed, they share a lot of them, almost all of them, with the Fourier transform. With some modifications here and there. For instance, if we want to do linearity, which we already seen it. Okay. Linearity of a guy like this should be equal to a1 times Laplace transform of f1 plus a2 times Laplace transform of f2 of t. Pretty simple. Pretty simple. Now, another thing we can do is something like this. Let's see, what if we want to have or calculate the Laplace transform of e to the power negative at times ft. How can we do this? Well, if we get overwhelmed we can think about the definition. Okay, definition is ft times e to the power negative at. This is the function we're interested in. Times e to the power negative st dt. So what is it? Sine integral ft. And we have two exponential terms that we can combine, right? I can combine, so this is plus. Now, Laplace transform of ft is almost the same, but on the shoulder of this Euler constant, instead of s plus a at s. So in other words, we're replacing s with s plus a. If we're sinking this s, let's say we use capital F of s to denote the Laplace transform ft, then this guy should be equal to what? Same function, okay, same function, but with s replaced by s plus a. Do we have any illustration? Yes, we just did it. We have cosine bt here. We have e to the negative at times cosine bt here. Okay. What else do we have? We have here s over s squared plus b squared. Now look at this one. The numerator s replaced by s plus a. In the denominator, when we have s squared, is replaced by s plus a squared. So the substitution works perfectly. S with ft replaced by s plus a, or this exponential discounted function. Okay. What others we can think? We have in fact seen this what we call the real shifting property earlier, and it works like this. Let's assume we have a function and we only care about its behavior from time 0 to infinity. And now let's apply a time delay to it. To apply a time delay, whenever you see a t will be replaced by t minus t0. And let's assume it's a delay, so t0 is positive. We don't go into the negative time period. So what's going to be the Laplace transform of this delayed signal? This delayed signal. Now, as a matter of fact, without the proof, we can refer to the proof in the text, but it's very easy to find out. It's very straightforward. It's going to be what? It's going to be the Laplace transform of ftut, or the undelayed function, right, times e to the power negative s times t0. Okay, and we have seen it already. What others? What others? Time differentiation. We've done it earlier before, so let's do Laplace transform of the derivative of a function with respect to t. It's going to be the Laplace transform of the function times s minus f of 0 at time 0 plus, meaning right after time 0. What about higher derivatives? This is generally a one derivative. The higher derivatives is easier to find out as well. So what we can do is apply this property multiple times, whereas in the second derivative, what do we have? Apply this property from second. Let me do first, so that one is the derivative of the other, times s minus f of t should become, if you look at this property, this guy and this guy should be the same guy. So since we have a derivative here, it should be followed by a derivative here as well, but evaluated at time 0 plus. So df t dt evaluated at t equal to t. Now we can move one step further, because here you have the Laplace transform of the derivative, and this is the Laplace of transform of derivative. So we can plug in the right hand side of this equation to replace this special. And what we're going to obtain is the following: Laplace transform, Laplace transform. And multiply it by s here, and this s will become s squared. So s squared times Laplace transform of f of t. And you have one additional term at the end. This guy will be multiplied by s. So it'll be minus s times f of 0 plus minus the last guy here. And write it as f prime as 0 plus. Prime means we take the derivative of the function with respect to t once. Now in general, we can do it not for 1 or for 2, but for n. And we'll apply this philosophy. If it's first derivative of s times it, second derivative of s squared. So if nth derivative issue has s to the power n, raised to the power n, times the Laplace transform of the original function f of t. Okay. Of course, minus s n minus 1 times f of evaluated 0, and then first derivative evaluated times 0, second derivative evaluated times 0, so I have double prime here, so on and so forth, so up to f evaluated at time 0. So we'll take the derivative n minus 1 times. How do we know, or how do we, is there any example to illustrate this property? Yes, we have done it already. Remember, we have our sine function just studied a page earlier, right here. B over s squared plus b squared. And cosine function and sine function are related by the derivative. The relationship is as follows. D cosine bt dt is equal to sine bt, but since we have b, it has to be taken care of. And because cosine functions start decreasing, so at times you have to have a negative sign here. What's the Laplace transform of cosine? It's s over s plus this. Okay. Now, I will proceed next is to say, oh, I want to calculate d cosine bt and dt. So it's going to be s times s over s squared plus b squared. So it'll be s times the Laplace transform of cosine function minus cosine function evaluated at time 0. Since 0 and 0 plus, cosine function is continuous function, doesn't make any difference. So, and cosine evaluated at 0 is equal to 1 here. This guy is equal to 1. So altogether, it should be s squared over s squared plus b squared. Minus 1, which is b squared. Okay. I forgot the negative sign. Just the minus 1. And the right hand side of this equation, negative b sine b. Using our linearity, we have sine b here with plus negative, when multiply negative b, this is what. So left hand side and right hand side are exactly equal to each other, which is perfect illustration of the time differentiation property. Time differentiation property. Now, after differentiation, we want to do integration. And since we have the unilateral, the single-sided Laplace transform, it's actually a simplified version of the Fourier transform in this way. So let's assume we have two functions. We know the Laplace transform of f of t. Okay, let's say this is given. I want to do a Laplace transform of this integral. And again, when we do the integral, we select the lower limit to be 0. This is the start of our observation. And to a certain time t, f tau deta. So we integrate this f function from 0 to t. And it can be proved that this is equal to 1 over s times the Laplace transform of f of t. Okay, which is pretty simple, which is very easy. Okay. Additional properties related to this. We have 3 of them, the additional properties. The first one is the S-domain differentiation. Before we have the time differentiation. Here we have the time domain, S-domain. differentiation. So since we're talking about estimated differentiation, we'll have to take derivative of the Laplace transform. So let's first assume, as usual, that the Laplace transform of f of t is equal to capital F of s. Simple. Now, if we want to take derivative of fs with respect to s, okay, and let's assume we want to do the inverse Laplace transform of this. The corresponding time domain function should have a certain relationship with the original f of t. The question is what is it? What is it? And as a matter of fact, this can be proved that using integral by part, we can prove this to be true. Let's multiply t over it. So we're taking a derivative. Okay. Now we can do an illustration of this property, which sometimes could be interesting. For instance, if we go to table 7.2, we'll see an example of t times e to the power negative 8 in the table. The Laplace transform of this guy is given as 1 over s plus a squared. Now, if we use the property given here to estimate differentiation, how do we obtain it? What we do know is if we take the Laplace transform of a simple function e to the power negative at, it's pretty clear it's 1 over s plus. Now, since the difference from this guy to this guy is we multiply t in front of it, the relation between these two should be related by the differentiation in time estimate. So we should take the derivative of this guy with respect to s. And since we have a negative sign on this side, but we don't have a negative sign here. So what we can do is, let's apply this negative sign on both sides of this property. Okay, like this. In other words, we want to take the time derivative. We'll take the negative sign in front of it. And let's see if these two are equal or not. We have our negative sign. It should be s plus a squared, since 2 to the negative 1 should be negative 2. And will be negative 1. So arrange the terms, and eventually we'll find out this exactly equal this one. And these two are equal. So, what does this mean? This means if we have a certain term, with t multiplied by with a certain function, we can always find the corresponding Laplace transform relatively simple. Okay? The other two properties we're going to explain here, that's a little different from the ones before. The ones before is trying to find the Laplace transform of a time function, or the inverse Laplace transform of a certain s function. Now what we're going to do is to do some limit. So one is called the initial value theorem. The other is called the final value theorem. The initial value, of course, is going to be the initial value of your function. Evaluate at time zero is our initial observation time point. But because we start the system at time zero, so we want to make sure we're evaluating the initial value at 0 plus. So on the right hand side of the time axis, it's going to be equal to the limit of s goes to infinity of s times f of s, where f of s is the Laplace transform of f of t. And the way to prove this is through definition and the fact that the Laplace transform of the differentiation is calculated as this is the Laplace transform of df of t and dt, right? And this is equal to what? Integral. Integral of a certain function, we don't care what this function is, time to the e to the negative st dt. And since we're letting s go to infinity, here is r minus s. When s goes to infinity, this whole thing will go to 0. If this thing goes to 0, everything goes to 0. So the right hand side will become 0 as s goes to infinity. If the right hand side goes to 0, okay, apparently these two are going to be equal. This guy and this guy should be equal to make everything 0. And of course, the term with s is evaluated when s goes to infinity. This is our initial value theorem. We have initial and we should have value final as well. Now, the final value theorem is interesting because what does final value mean? Final value means we're evaluating our function f of t equal to plus infinity. What does it mean? It's the steady state value of that. Okay, in the same idea. We're going to let, instead of asking this guy's s goes to infinity, we're going to ask s go to 0. Okay. If s is going to be 0, then we still calculate s times f of s. But now, remember we have s f. We have this before. Okay. And we have the function here. This is a plus sign. And since s is 0 here, s equal to 0 means this whole thing should go to 1. So we don't even have to write it here, just 1. Now, what does this give me? This should be f of t equal to plus infinity minus f of t t equal to 0. Of course, we evaluate t equal to 0 plus. And this is when, of course, evaluated as s being 0. And if we compare the left-hand side and the right-hand side, you have f of 0, you have f of 0 here, cancel each other, and the only two terms left is this guy, and the steady state or the final value of my function. That's why we have this final value here. It's pretty easy, pretty simple. All we do is we take s times my Laplace transform, evaluate it at s equal to 0, and evaluate it at s equal to infinity. Something that's very interesting is if this whole thing is infinity, okay, we'll give an example later. It means this function has no steady state at all. So, example. Let's take the unit step function, u of t. And we know the Laplace transform of the unit step function is 1 over s. So, using initial value theorem, we want to evaluate it at s times f of s at s equal to infinity. And since s times f of s is just 1, initial value is 1. Final value, similar, we value s equal to 0. But it doesn't matter, s here and 1 over s here will cancel each other, so you always have 1. Always have 1. Now, let's change 1 a little bit. Let's change it to f of t equal to t, our rent function. The Laplace transform of the rent function is 1 over s squared. We can see this in the table 7. What does this mean? This means if we use the initial value theorem, okay, of the s times 1 over s squared, evaluate as s equal to infinity, we have 1 over s, okay, one of them is cancelled, evaluate s equal to infinity, which is 0. So here should be f of t plus 1. So it means the initial value of my function is 0, which makes sense because this guy is right here. This is 0, this is t, this is f of t equal to t. Okay? So start as from the origin 0. Now, the final value, the steady state, quote unquote steady state, will be still 1 over s, so here s plus times f of s, evaluated as at s equal to 0. But this guy will be infinite. That's going to be infinite. Does it make sense? Of course, this function has no steady state at all. So that's why you have this infinity in the Laplace transform final value theorem. Which makes sense.